So now it is really my absolute pleasure to introduce our first robotics seminar speaker for the series, Professor Rebecca Kramer-Bottiglio. Professor Kramer-Bottiglio is the Associate Professor, John Lee Associate Professor of Mechanical Engineering at Yale University. She has received numerous awards. I'm going to highlight just a couple. The NASA Early Career Award, the AFO-SOAR, and ONR, the Young Investigator Award. She was named 30 under 30 list for her work on liquid metal-based stretchable electronics. The PCASE, which is the Presidential Early Career Award, and most recently one of NSF highest honors, the Allen T. Waterman Award. I'm so excited, and one of my favorite thing about every time I see Rebecca's work, just the creativity and the incredible interdisciplinary approach to these really cool robotic systems, but just an awesome approach and like a new perspective to everything that she works on. So I'm so excited.
Thank you so much for that introduction. I didn't realize I was the first robotics seminar speaker of the semester, so I feel quite honored. Thank you so much for inviting me to speak here today. I'm really looking forward to spending the day with you all. So I'm excited to tell you a little bit about our thoughts, my group's thoughts on soft robots that evolve on demand. But before I get into that, I want to start with the robot cliche. When you ask people to conjure up an image of a robot, most people think of something like this. These are rigid machines that perform a repeated task. They're very good at what they're designed to do, right? These are fast and strong and precise. But what they are not is safe for human-robot interaction. You don't see people working alongside these robots. And they're not adaptable. You don't see these robots adapting to changing tasks and environments because that's not what they've been designed to do. But when we all imagine robots for the future, I think we all imagine something more like this, like animals, like ourselves. We are incredibly adaptable, right? We readily adapt our body configuration and our behavior to different tasks and different environments. I can easily transition from manipulation tasks to locomotion tasks. I can transition my body properties, right? I can stiffen my muscles and soften my muscles in order to perform both forceful and gentle tasks. So how do I do that? How do you do that? How do animals do that? Well, I noticed something when watching all of these videos. All of these animals look at least partially soft. So let's take a deeper dive into that observation. Okay, here's a plot of all known animals in the world, just over 1 million at the time of this data. And just to put things into perspective, we as humans are in the mammal category, which is this tiny sliver of all known animals. And yeah, as it turns out, all known animals in the world are at least partially soft. There are no known animals that are completely rigid, which is in contrast to the way that we typically design machines and robots. And if we look at this even further, we see that over half of all known animals are completely soft, so contain no rigid elements whatsoever. So there's certainly some things to think about when you're thinking about completely soft animals. You can think about jellyfish that live in the water or worms that live in the ground. They need to be supported by their environment. We as humans are a fairly large animal that lives on the ground. We require some rigidity, our skeletal structure, to keep us standing up. But as a case study, humans on average are only 15% bone skeletal structure and 85% soft and fluid materials. So when I first heard this, I thought, wow, there has got to be something to that. Is it possible that our soft material composition plays a role in our ability to interact with and adapt to our environment? And if so, could soft robotic technologies be part of the solution to the adaptability problem for robots? So I am by no means the first or the only person to start thinking about these questions, thinking about soft robotics in this context for adaptation. And soft robotics is a rapidly growing field that has lots of other benefits potentially outside of adaptation. So soft robotics, rapidly growing field. Lots of pioneers who have been looking at these technologies for potential adaptation, but also other potential benefits. So I want to showcase some of these benefits here. So in the first video that you can see on your left, there's a soft robot that's walking out into the street. It's a locomotion system. It gets run over by a car. It's able to continue locomoting despite this impact owing to its soft material composition that's absorbing those forces. In the middle, you can see a soft pneumatic gripper. It's able to grasp diverse and delicate objects, owing to that soft material conforming around the objects. And on your right, you can see a wearable system, a wearable robot that could potentially augment load capacity for the wearer or increase efficiency of motions for the wearer while conforming around their body, the soft material conforming without restricting the natural mechanics of motion of the wearer. However, all of these robots are task specific. So we talked about locomotion and manipulation and wearability. They're designed for a specific use case, and they would not perform well for any application outside of that intended use case. So the locomotion system, for example, would not perform well in a manipulation context. So the grasping robot would not perform well in a locomotion context, and so on. And so my question is this: can we design more adaptive robots? Can we use these emerging soft robotic technologies to build robots that can adapt in their morphology and property and behavioral control policies to changing tasks and environments the way we do? So this is a central question that I've been asking for a long time. That kind of is the focal point of my research group and my research program. And we come at this from the perspective of materials and thinking about soft robots not necessarily as mechanical assemblies, as assemblies of discrete components of sensors, actuators, structures, controllers, and putting those together, but rather as multifunctional material systems. And so one of our core competencies is we're really good at emulsifying things. We can take responsive materials and break them down into discrete components where we can then use them for different manufacturing processes. So you can imagine particle concentrations at high concentrations being used for printable slurries and at low concentrations being used for more drop-on-demand style printing. Or we can also mix these functional particulates into other functional materials in order to create multifunctional composites, and then use all of these new manufacturing processes and multifunctional materials in emerging soft robot platforms with an eye towards adaptive morphology and behavioral control policy for changing tasks and environments. So here's just a few of the robot platforms that we've been thinking about recently. And I'd love to tell you about all of them, but I don't want to keep you here for so many hours. So we've now reached the adaptive part of the talk. I have prepared modules on each of these 4 topics. And historically, I only have time to talk about 2. Without keeping you too long. So I'm going to let you vote on what you would like to hear. You choose your 2 topics, and then we'll dive in. So I'll give you a little bit of a snippet of each of the topics that you know what you're voting on, and then we'll get to a voting process. So the stretchable electronics module is about liquid metals. It's using eutectic gallium indiums and gallium indium alloys that we initially started looking at for sensors for soft robots, but then kind of inadvertently discovered a formulation that has a very suppressed strain response. And so we use this strain insensitive formulation in order to port traditional electronics and computational circuits into soft stretchable forms. Robotic skins is one of the oldest topics on this list. It looks at planar elastic membranes with embedded actuation and sensing that we can wrap around inert deformable objects in order to turn them into robots from the surface. Robotic fabrics, again, looks at planar surfaces, but fiber-based, where we're looking to create functional fibers that serve as actuators, variable stiffness materials, and sensors, while retaining the neat fiber architecture and mechanical properties of the fabric. And then finally, this broad category labeled morphing robots will focus on an amphibious robot, a turtle and tortoise-inspired platform with morphing limbs that morph between a flipper state and a leg state for efficient locomotion in water and on land, respectively. Okay, so with that snippet, I'm going to initiate voting. And I thought, based on the size of the room, sometimes with smaller groups, I can do just kind of hand voting. But we can vote by applause, and I have a decibel meter app on my phone. So I am going to have you applaud for each topic, and then whichever gets the loudest applause, those are the topics we'll go with. So with that, if you are interested in hearing about stretchable electronics, please applaud. All right, that reached a maximum of 80 decibels. Okay, and robotic skins. All right, that was 82, so front runner. Okay, and robotic fabrics. 80.3. And finally, morphing robots. strong winner here for morphing robots. That went up to 88 decibels. Nice job. Okay, this is fun. This isn't what I predicted. I had predicted that people love this topic. This one almost gets chosen. But I thought that there was a contingency of people that might vote for stretchable electronics and robotic fabrics. Some of you did, but the robotic skins won out. So let's start with robotic skins, and then we'll do our amphibious robotic turtle. Great. Okay, so like I said, this is one of the older topics in this mix. Robotic skins was one of the first projects that my group started working on when I started my faculty position. And so it was really serendipitous. I started my faculty position, and then there was this call from NASA. There was a solicitation from NASA. NASA was looking for specifically soft robotic technologies to address a challenge that they were having. They were interested in using soft robotic technologies for multifunctionality in extraterrestrial missions. So when you think about it, you have to send things to the moon and Mars and other extraterrestrial bodies, and they perform different tasks, right? They need locomotion systems, they need manipulation systems, they need all sorts of systems that perform different tasks, and they have to create different robots for all of those different tasks. And it costs a lot to send all of those different systems into space, right? It costs volume, it costs weight, all of those things contribute to the overall cost of transport. And so they were interested in reducing that specific cost. They were interested in lightweight systems that could be compacted and deployed and potentially used over and over for different tasks in order to reduce the cost of transport. And so I had an idea, and this is the idea that I pitched. Robotic skins. What if we could turn skin-like membranes into robots? If we could make these elastic planar membranes with embedded sensors and actuators and computation structures, all of the things that we need, but within this stretchable membrane that can be wrapped around inert deformable bodies and turn things into robots from the surface on the fly. So in this case, there's a kind of simple schematic of a potential robotic skin. We have actuation layers, which are drawn as lines. Those are meant to be linear contracting actuators. We have different sensory layers that might be sensitive to strain in certain directions or pressures. And then we can put those all together, wrap them around some soft body. So in this case, it's meant to be a balloon. So we wrap a robotic skin around a balloon, and if we wrap it so that the actuators are radially wrapped around the balloon, and then we sequentially contract those actuators, we get something that looks like peristalsis. And we could take this balloon and put it on the ground, and it might look like it's performing peristaltic locomotion. Now we can take this robotic skin off, so we can remove it from the balloon, reorient it 90 degrees, and reattach it. Now those linear contracting actuators are along the length of the balloon rather than wrapped around radially. And so when we sequentially contract them, now they'll bend the balloon. And so you could see this kind of bending motion. You can imagine if you take this robot and put it on the ground, that you might see something that resembles inchworm style locomotion. And so you can start to think about how you could use robotic skins and skin-based control in order to create robots on the fly that have different motions, different modalities of motion, and different types of locomotion, perhaps, for various terrains and locomotion robots. Okay, so I wrote up a proposal. It was actually the first proposal I ever wrote to NASA. They reviewed it, they said yes, and off we went. So this was one of our first projects. And we had to build everything from the ground up. So we said, okay, we're still thinking about these things as a mechanical assembly right now. We have these structures with actuation layers, sensory layers. And at the time, I was coming out of my PhD. I had worked a lot with sensors, and so we began with the sensory layers. That's what I'm going to start telling you about first. Okay, so our initial sensors for the robotic skins were this conductive composite-based capacitive sensor. It's an elastic capacitive sensor. So here you can see kind of what the capacitive sensors look like. It's a layup of electrodes, dielectric electrode, and you strain it, you get a capacitive response, and then we hook that up to a circuit to transduce capacitance into voltage in order to track the strain response. So how do we make stretchable electrodes? That was the initial challenge that we were looking at. And in the video, you can see how we started to do that. We used an exfoliated graphite flakes as the conductive particulate within an elastomer to make stretchable electrodes. And so what we did, it's actually a somewhat simple process. We took chunks of graphite and we soak it in a solvent. And then we put the solvent soaked chunk in a really hot environment, in a hot crucible in this case, and it vaporizes the solvent, right? The solvent goes above its boiling temperature and it starts to push the flakes of the graphite away from one another, which is what you saw in the video. So that's the exfoliation process of these graphite flakes being formed. And then we can take these flakes and mix it into a pre-cure polymer, and we can rod coat it, make films of it, and cut out these capacitive sensors. So you could use a 3-layer sensor. We make a 5-layer sensor. We just add another dielectric and electrode layer in order to protect the sensor from noise. Okay, so let's look at how these sensors perform. So we have a nice linear response. This is one of the benefits of capacitive sensing and stretchable capacitive sensing. Our capacitance response to strain is typically very linear. We have an expected nonlinear mechanical response to strain. It's a fully elastomer layup, so that's highly expected. Our sensors, this particular one is, it operates up until about 375% strain, sometimes higher. So we think it's very accommodatable to the types of soft robots and types of strains that we would be experiencing. And we also looked at drift over hundreds of thousands of cycles. So we cycled our sensors to 100% strain for 100,000 cycles, and we saw very little drift in the gauge factor, which is a measure of the sensitivity of the sensor. And working alongside NASA, they also encouraged us to look at temperature variations, environmental radiations overall, variations overall. And so we did look at some slight temperature sweeps between close to room temperature and a little bit warmer, and again, saw a lot of stability in the gauge factor or the sensitivity of the sensors. So I will say before moving on that we have developed these sensors quite a bit further since this initial design. We've added in addition to the graphite flakes, we've added in liquid metal particulates. So we've made it a multi-phase composite. And this actually evens out the thermal conductivity throughout the electrode. The electrical conductivity and the percolation is much more uniform throughout the electrode. And so this has increased our linearity of response, especially at very high strains, quite a bit. So that's just some more recent work that we've been doing with this. Okay, so with confidence in our sensors, we can now put them together with actuators and start to realize the robotic skin concept. So here are just a few of the initial prototypes that we made. So it's really important to think about robotic skins not as a specific embodiment. So it's not a specific substrate material, a specific layout of components, specific actuator choice or sensor choice. It is an elastic membrane with embedded actuators and sensors. And it could be any choice of membrane. It could be any choice of actuators and sensors as components and any layout of those components. So we wanted to showcase that here by creating a couple of different prototypes that realize this robotic skin concept. The first on the top is a rectangular robotic skin. So we used an elastomer substrate. Stand by the podium, sorry, I feel like I'm wandering. So we used an elastomer substrate as our carrier substrate, and then we embed our sensors within the substrate. So you can't quite see them. They're behind these pink McKibben actuators, but you can see the signal conditioning boards sticking out. And those are attached to our sensors. Again, they're transducing capacitance into voltage. And then what you can see more clearly are the McKibben actuators. So these are pneumatic actuators that linearly contract when we inflate them, when we increase pressure. And this is a parallel layout of components. So it's lendable to single curvature bodies, things like tubes or cylinders. So you can take these skins, these rectangular skins, and wrap it around a cylinder of foam, for example. That's what's imaged here. And we can see that same kind of idea from the first ideation slide, that wrapped in one orientation and sequentially contracting those linear contracting actuators, we would get a compression of the foam. And then if we take off the skin and reorient it 90 degrees, reattach it, we can get a bending of the cylinder, not of the skin, of the cylinder. And then attaching a few of these together. So here, this is a long tube of foam, and we've taken 3 rectangular robotic skins and just put them all together in parallel. And you can see this kind of multi-segment soft continuum arm. So then a second embodiment that we created of the robotic skins uses a different substrate. So instead of an elastomer substrate, we went to a fabric substrate. We again use our elastic capacitive sensors. In this case, we print the sensors directly into the fabric. So slightly different manufacturing process, but overall the materials and the capacitive sensing is the same idea. And then instead of McKibben actuators, we use shape memory alloy actuators. So shape memory alloys It's a metallic alloy that can go through a crystalline phase change between martensite and austenite when heated. It can be programmed to remember a shape. So what we do is we buy it in wire form. We just buy these wires, and then we program it to remember a coiled shape. So when we heat it and it goes through that crystalline phase change, it remembers the coil and it contracts into a coiled shape. We can get about a 50% contraction, and then it can be pulled back to its original configuration. You heat it again, it can be contracted again, remembering that coiled shape. And the contraction can happen through joule heating. So we just apply a current and the alloy joule heats. So here we use a triangulation of components, which is lendable to compound curvatures. So we can get away from single curvatures like these cylinders of foam. We can wrap the skins around things that look more like spheres. So in this case, we use a 6-bar tensegrity. This is not a sphere, but kind of a ball-like shape in a tensegrity form. And we attach 20 of these skins to the outside, and we're able to take a completely inert tensegrity structure and control it, do punctuated rolling locomotion from the surface. Okay, yes?
So both the McKibben and the shape memory alloy are sort of notorious for being a little slow.
Yes.
Is that right? So,
You can see their time scale of actuation actually on this plot. They are slow.
so any thoughts on how to do the actuators faster?
Yeah, so I will say that, so I agree, they're both responsive materials which are known to be slower. Of the soft actuator technologies that we typically work with, pneumatics is on the faster side. So we typically put pneumatics in the highly reliable, fast, strong category relative to a lot of the other materials that we work with, which would include shape memory alloys and liquid crystal elastomers, for example. But relative to traditional motors, they're going to be slower just because there's a time associated with fluid flow and fluids moving around the system. Yeah, it's an acknowledgement of your observation. I don't have a mitigating solution to that problem yet. Yeah. But it's a really good point, and it's demonstrated here. So I wanted to show a bit of. Oh, sorry, I didn't see it. Yes, go ahead.
Yeah, I wonder, can you, so it's the automatic skin, can you layer them?
Yeah, we can. It's a great idea, great observation, and I show something a little bit similar later. We can layer them. Now, the one thing that we had a lot of challenges with, so we have this idea that robotic skins will be these incredibly planar skin-like membranes, right? But you can see based on the components that we've chosen that they're a bit bulkier than that. And as you start layering them up, they do accumulate bulk, and it impacts the mechanics of the system a lot. The other thing is, as we're attaching these skins to a body, we have to have very good adhesion between the skins and the body for that force to actually impart to the body, right? So a lot of times we'll see if we have imperfect adhesion, if they're not perfectly connected, then some of the force is lost through slipping around the surface. And as we accumulate skins on top of one another, that problem becomes exacerbated. The force that we're trying to apply might be very far from the body that we're trying to apply it to. Yeah. Hi. It's great to see you.
Just the thing, even the body, you can have an entire thing of skins.
Yes.
And on this arm, where you have all the layers are active, and when one layer is active, the other layers begin as the body and the stretchable.
I love that idea. We, in a video that's coming a little bit from now, you will see that we have one skin that's performing without attachment to a body, but it's not attached to other skins, as you're suggesting. I think that's really clever, and we haven't explored that rigorously, but I would love to do that with you. Other questions? Great questions, guys. Okay. All right, so I want to show a bit of closed loop control now that we talked about sensors and actuators. Let's just make sure they're communicating well. So we did these two demonstrations. We have foam cylinders, so soft cylinders, and we wrap our robotic skins around those cylinders. The robotic skins wrapped around both of these cylinders are rectangular. They have a parallel configuration of components. So our actuators and our sensors are along the length of the cylinder. And we position our sensors on two different sides. So in this case, we position our sensor on the inside of the contraction. In this case, it's positioned on the outside of the contraction. So it's, in this case, the sensor is actually contracting. In this case, it's stretching. And in one case, we're using pneumatic actuation. That's over here. You can see the time scale of actuation is quite a bit faster. And in the other case, we're using shape memory alloy actuation. You can see the time scale is quite a bit slower. And that's reflected from the actuator choice. In both cases, we command the cylinder to do just a step function of contraction through a bend. We say bend, 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 and then at a certain point, we ask it to sequentially come back up, back up, back up, back up. And that's what you see as the step function here. So we're bending, 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 and then coming back up. The solid line is the set point. That's what we're commanding the system to do. And then the dash line is what we're actually measuring, the position that we're measuring based on our sensors. And you can see that we're tracking the set point fairly well, even at both time scales, these longer time scales and faster time scales. Okay, so now we have some confidence in our sensors and our actuators and our ability to control the system, so we can start to realize the robotic skin concept. So this is in real time. This is not sped up. So that gets to, we think this is fast, but it's not always fast relative to other technologies. But here we have 3 robotic skins that we wrapped around this long tube of foam. You could use any tube of foam. This comes in packing materials. You can use a pool noodle. We've wrapped these around pool noodles before. We had that 3-segment continuum arm that was kind of dancing. If you look this video up online, there is music to it, so it's dancing to the music. So we take the robotic skins off, and then we can put them on 3 other bodies in order to achieve a different task performance, locomotion performance. So here I'm actually going to, let me see if I can go back a little bit and replay this part. So one robotic skin is wrapped around this cylinder foam. Remember, these are parallel configuration of components. So we are confined to single curvature bodies. And let's see. Yes, so in this case, we have these weighted end caps. So those of you who work with elastomers might remember we mix in cups. You pour part A and part B into a cup, and then you use it, and you have this stuff at the bottom that just kind of cures there. And we just took those out of the cups and pinned them on to the ends, and we made these weighted end caps for this grab and pull style of locomotion. Move it forward just a tiny bit more. And then in the middle, we have a bodiless one. So this is not attached to a separate soft body. This is a skin just locomoting on its own, but I like your idea of attaching multiple skins together. We will definitely look at that in the future. And then here we have a more inchworm style of locomotion. We've just used rubber bands in order to, sorry.
I had a question about the middle one.
Yes.
How does it go to go right? Is it guided by the wires? Because when it contracts and extends, it doesn't know whether it should go left and right or right. You know what I mean?
Yes.
So the wires are doing something.
You're right. I think, so in many cases with tethered systems, the locomotion function is heavily affected by the wires. And you're right, there's a lot of tethering going on here. We're controlling, we have tubing for the pneumatics. We have wiring in order to, deliver power to our transducing circuits, our capacitive circuits. So there's a lot of tethering going on here, and power is off board. So there certainly can be some influence from the wiring. We haven't untethered these systems yet. We did, I will say, I don't have a video of this particular one, but we do have, we did a demonstration where we put a light sensor on a robot that looks most similar to this one. So this one we just have the rubber bands and the laser cut. It's just a piece of plastic that's been cut to have bias feet so that it will move in bias direction during inchworming. And we attached the light sensor just to the front of it and then used a flashlight in order, we just told it to very simply follow the light. And then we moved a flashlight around and it followed the light. And it was also tethered, but it was able to make fairly, I'll call them agile turns and follow the light pretty well. So we know that there is some control that is beyond the tether. Did that answer your question? Okay, great. So the final thing I want to point out on this slide is that all of these demonstrations are intentionally very hacky, right? So like I said, we just, took out the pieces of elastomer that had been cured in the bottoms of cups and used pins to put them on, and we use rubber bands here. And that is all in line with the robotic skin concept. We wanted to deliver something to NASA that they would be able to just grab whatever they had available, in situ material, crumpled pieces of paper, rubber bands on board, and that people would be able to build robots for different types of locomotion or different types of manipulation performances or grippers, just using whatever they had. So that's why we very intentionally made these out of readily available materials. Okay, so now we can return to our 3-segment continuum arm and turn it into something that looks a little bit more like a gripper. So in this case, we have two plastic plates, and we've taken one of our robotic skins, and we simply contract it between the plates so that it grabs an object, moves it to a desired location. Here we took that one gripper off and added another gripper. So it's the same 3-segment continuum arm here, but here we have an active finger and a passive finger, and this is just made out of cardboard. And again, we just grab an object, move it to a desired location. So this shows how we can use the same exact skins across a manipulation platform, a gripping platform, and a locomotion platform, or several locomotion platforms. Okay, and now we can look at our triangular skins. So I talked about this a little bit before. Yeah.
Did you, this might go to Christine's point, did you ever try wrapping it in a kind of angular way so you could cause it to twist?
Yes. Oh, we actually just published a paper on this. I had a student that looked at, angles of actuators and looking at torsion. The modeling became slightly more complicated. We had to relax some assumptions in our initial models about constant curvature. Yeah, exactly. In order to couple constant curvature assumptions to torsion. But yes, we've started looking into it. It is possible. It's a little bit more challenging for us to do predictive modeling on placement of the end effector, but efficacious nonetheless. Great question. All right, so here are the triangular skins with the triangulation of components. We decided to put them on a 6-bar tensegrity. This was largely influenced by our collaboration with NASA. So we were working alongside them on this project, having tight collaborations with NASA Ames in particular. And at the time, they were really active in a project called SuperBallBot. Maybe some of you have heard of it. It was a robotic 6-bar tensegrity. So they had a structure that looked like this, except it was very large. I'll say this tensegrity that you're seeing in this video is it's desktop scale. It's about this big. SuperBallBot, the one they built at NASA, is about my height. It is massive. And it is fully robotic. So they change the lengths between the cables that suspend these rods in order to create punctuated locomotion. So we were very inspired by them and working alongside them. We took a fully passive 6-bar tensegrity. So there's nothing robotic about this one. And we took 20 of our robotic skins, patterned them around the surface, and then actuated it, achieving the same kind of punctuated rolling locomotion, but actuated entirely from the surface. All right, so then we can take these skins off and use them in a totally different context. So here we've placed them on the back of one of my former postdocs. This is Jordan Booth, and he's doing a great job here. So we've just used double-sided tape in order to attach the robotic skins to his back. And we've aligned the sensors along his spine, and we've programmed them so that once they stretch beyond a threshold, as he's slouching, the sensors will stretch. Yes, question.
This is very interesting. I have a question about the integrity. When you change the length of the cables, how do you maintain stability? Can you make some comments about the stability of the system?
Yeah, so from a robotic tensegrity standpoint, there's a really large amount of literature on robotic tensegrities, and I don't want to try to represent all of it. People have used really different technologies towards this. But I would say the most common approach, this is the most common morphology, a 6-bar tensegrity. We're actually working on a 3-bar tensegrity, but it has a different morphology than this. I think the symmetry of the 6-bar makes it really appealing. And so most of these are actuated through a winch and cable mechanism. They're usually larger in order to actually accommodate that hardware. And so tensegrity is tensile integrity. Sorry if I wasn't clear about that initially. It means that there are rods that are suspended away from, so none of the rods are in contact with one another. They're suspended away from one another and in equilibrium via cables and tension. And so those cables are what's connected to the winch and cable mechanism. And so basically via spooling mechanism, it will shorten and elongate the cables in order to change the morphology of the overall structure. And that causes an instability, which causes it to roll onto a new face. And so that's why we get this punctuated rolling locomotion where it rolls onto a new face, and then you shorten another cable, which causes it to roll onto a new face again. Does that answer your question, or was that not the intention of your question?
Yes, it does.
Okay, great. Wonderful. Okay, so let's look at wearables again. All right, so here, Dr. Booth has our robotic skins attached to his back with double-sided tape. We've programmed the sensors to communicate with the actuators. So once they stretch beyond a threshold, so he he slouches, it stretches the sensors. The sensors go beyond some threshold that we've set, and you'll see in the data that's about to pop up over here. There it is. Okay, so there's our sensor data, and whenever he slouches, it goes into this stretch position, and that communicates to the actuators that they should start pulsing. So the actuators, you can see they pulse to communicate with Joran that he should sit back up. So I'm commonly asked whether these actuators are actually corrective of the posture, and they are not. But I will say, if you come to my lab, please ask for this demo. It kind of feels like a massage. I think it's very pleasant. Might actually encourage slouching a little bit, but I don't know. Come and try it and let us know. Great. Okay. So hopefully I've been able to convey to you this kind of vision that we have of modular soft robotic skins that can, we can have them in different layouts and they can accommodate different curvatures of bodies, but we can mix and match them and apply them to different soft-bodied materials in order to create robots on the fly. So we can apply them to these long tubes of foam and different types of gripping mechanisms in order to create manipulation platforms. This is the one I didn't show you a video of, but you can see the light sensor that we put on the front of it. That's the image of the light sensor. And so we can control it a little bit. We can put them on, things like these 6x10 segreties to create rolling locomotion robots, and then take those exact same skins off and put them on a person, create a wearable system. And so the whole idea is to be able to use and reuse the robotic skins for different tasks, to be able to complete different tasks. So moving on, as we got to this point in the work, and one of the things that we struggled with was the human handler part of it. So all of the videos that you saw require a person to actually come in and position the skin, attach the skin, remove the skin, put it on something else. So there's definitely a person in the loop here that's making a lot of decisions and doing the design. And we were thinking about autonomy in terms of variable morphology and variable task performance without a human handler. So I had this really fantastic phone call with Josh Bungard. He's at UVM. This was years ago, where we were talking about robotic skins. And he had this idea to wrap them around plastically deformable materials. He said, you can wrap them around clay. Can we use robotic skins wrapped around clay and sculpt materials from the surface? I said, wow, that's a great idea. And so we started jumping into that a little bit. So this overall concept of wrapping robotic skins around, say, a sphere of clay, any plastically deformable material or clay-like material that can be molded from the surface, applying surface strains and pressures. And kind of just like a sculptor would take a block of clay or a ball of clay, be able to apply surface strains entirely from the surface and mold it into any morphology. And we wondered, can we do that with robotic skins? You can imagine robotic skins molding the underlying body into something that might be rolling locomotion and then elongate into something more snake-like, that can cylindrical-like, that can slither, or inchworm, or undulate, and then maybe even grow appendages into something that looks like a quadruped. It can navigate maybe sandier surfaces. So we did a little bit of preliminary work toward this idea. This was one of our only instantiations that also used layered skins. That was a question from earlier. Can we layer the skins on top of one another? So in this particular demonstration, we have a clay-like material. This is actually Model Magic. Maybe some of you have used it. It's not a technical clay, but it is clay-like in that it's a moldable material. And it's the white center that you see. So the white center is this Model Magic cylinder, and we've wrapped it in 2 robotic skins. So we have a pneumatic robotic skin that sequentially inflates, and that's what's causing the rolling locomotion of the cylinder. And then we have this cable-driven skin. So you can see that one on the surface, you have blue cables, and we can pull those cables in order to cinch the entire body throughout the length. And so the demonstration that we completed here was we have this rolling cylinder. It's rolling on this flat ground, and it encounters an obstacle. It encounters this rock, and it can't roll over the rock. Well, in normal path planning or obstacle avoidance, you would say, okay, we have to figure out how to get around the rock. Let's change the path. We're going to go around it this way. So you might back up and go this way and go around it, or you could go the other way. It becomes a path planning problem. And so we decided to instead change the morphology of the robot. So we took our cables and we cinched them in the middle, and we changed the morphology from this more cylindrical shape to a more dumbbell shape. And that allowed us to roll over the rock. So we were able to keep the same path and the same gait. Without changing path or gait, we avoided the obstacle. So this is a very low level demonstration, but I think it to me shows potential. We're very interested in using this potential of robotic skins wrapped around clay-like materials to adapt the morphology using these other approaches that would be complementary to traditional path planning and gate transitions. Okay, and then as a final thought in this part of the talk, still working alongside NASA, we're still working on, this is an active project that we have right now, actually an active funded project that we're working on. We thought, okay, well, if we're gonna be using clay inside the robot anyway, why not use in situ material? We're gonna go to extraterrestrial environments where we know there are clay and sand deposits. Maybe we can use those things. We don't have to transport them. Again, reducing weight and volume during transport, use what's there. So we could take these robotic skins and deploy them as kind of parachutes that deploy very safely into the environment, and it can be transported flat and lightweight, really low volume, really lightweight. And then once they get there, potentially stiffen their leading edges. And I imagine these robotic skins being able to burrow into the ground and scoop up their own bodies, using in situ materials to create their own bodies, envelope around that material, and then perform tasks just as we saw in the previous slide. So this is something that we're working on right now. We're doing a lot of work towards variable stiffness materials in these leading edges and also studying burrowing, which is a new project for us. We're learning a lot about penetration forces through different granular media. And we're having a lot of fun with this. Okay, so with that, I will move on to your second voted topic, morphing robots. Okay, so this is a project that we started working on with ONR a few years back, actually about 7-8 years ago is when we started working on this. And it again started with a very specific challenge. ONR was interested in amphibious locomotion, multi-environment locomotion, efficient multi-environment locomotion. And so we started thinking about amphibious robots and how they currently do this. And what we learned is that amphibious robots typically fall into one of two categories. So usually you have an amphibious robot with a dominant propulsion system, one that is really efficacious in one environment. So say it has a propulsion system that's largely optimized for land locomotion, and then can operate in water, but it's less efficient in the water environment. So it can be amphibious, but it has a dominant environment where it's more efficient in one environment. Or the second category is amphibious robots with two dedicated propulsion systems, one for water, one for land, and then the robot will retract and deploy whatever propulsion system it needs based on the environment that it's in. But this means that it's always carrying around a propulsion system payload. It's always carrying around one system that it's not using, and we thought that that might negatively impact the energetics of locomotion in each environment. And so we had this idea to create a unified propulsion system, a single propulsion system that leverages soft robotic technologies to morph the propulsor to be specialized in each environment. But this way it's not carrying around a separate propulsion system, it's using the same one, and it should be efficient in both environments. And so as I've been explaining this, you've been watching these two videos, so it will come as no surprise to you that we were very inspired by these two species. We surveyed land locomotors and water locomotors, and we identified sea turtles and land tortoises because they are morphologically very similar, right? Both are quadrupeds, both have a central shell, hull, carapace, and they differ primarily in their limbs. So they differ, sea turtles have these flattened, elongated, flexible flippers that are very specialized for locomotion in water. Land tortoises have rounded, load-bearing legs that are very specialized for walking on land. And with this inspiration, we thought, okay, we can build a single robot that has an immutable shell at the center, more traditional robot center, and really only morphs its propulsors, its limbs, between flippers and legs in order to achieve this efficient multi-environment locomotion. So this is exactly what we did. We created this robot that we call the amphibious robotic turtle, or ART for short. It is sea turtle and land tortoise inspired, and it has these morphing limbs. So the center of the robot, this 3D printed shell, which I'll talk about more in a moment, has all of the traditional robotic components housed in there and protected in there. And we have soft robotic limbs, which are variable stiffness materials and soft actuators coupled along the length of the limb that transition between flipper and leg configurations. So I'll go into a bit more detail about how all of these different components work. So here's our first iteration of the morphing limb. It's initially in flipper configuration. That's how we manufacture it. It's made of pneumatic actuators in elastomer. So there's 3 pneumatic actuators on this limb. There's one on the outside here, one on the back that you can't quite see, and then one in the tip that folds under. So that's the tip of the flipper. And as it folds under, that creates the foot of the leg. So that's what comes into contact with the ground in leg shape. And then we use a thermoset epoxy as our variable stiffness material. That's the clear material that you can see kind of going into the limb here. It's a thermoset epoxy. It has a glass transition temperature, decreases by about an order of magnitude in stiffness when we warm it above that glass transition temperature. And the way we warm it is using this co-located heater. So you can see a laser cut copper heater that's embedded within that thermoset epoxy. And so we simply apply current, joule heat the heater, it warms the epoxy, softens the limb, and then we can use our actuators in order to move it into the leg shape. We cool the whole system down so it holds the leg shape passively. And then when we want to go back to flipper, we simply apply current again, warm the limb, soften it, and it can use its stored elastic energy in order to return into its neutral flipper configuration. All right, so here you can see some images of our leg mode and flipper mode. There's pretty extreme change in the overall shape. Leg mode is, more cylindrical, rounded, and load-bearing. Flipper mode is very flattened, has a nice hydrodynamic profile. I won't show the lift and drag performance data here, but it performs pretty well. And then the way that we attach these flippers or legs, limbs to the robot, you can see that here. We have a 3D printed shell in the middle. We have all of our control systems, power supply, everything we need is housed in the center of the robot. And then each joint is made of 3 Dynamixels, 3 servo motors that create a 3 degree of freedom joint at each shoulder. All right, so let's check out the robot in some respective environments. So here we have the robot swimming in a backyard pool. This is actually my dean's backyard pool. Yeah, so we were collecting this data in the summer of 2020, which we all remember then. So we lost access to the Yale pool. The Yale pool was closed, and we were having a really hard time gaining access to any kind of public pools that we could do testing in. We were doing some testing over the summer at a pool club locally, but then it closed for the season. And then you can see in some of these videos that there's leaves floating. Yeah, there you go. You can see the leaves floating at the top of the pool here. So we were pretty desperate to continue testing, and our dean very kindly kept his pool open for the season, or late in the season, just to accommodate our testing. But it tells you a little bit about how cold it was, seeing those leaves floating up there. Nonetheless, we are swimming. So here the robot is in flipper state, has its limbs in flipper state. It's using flapping gates. These are lift-based propulsion gates. We also did some paddling gates, but I don't show them here because they don't look quite as beautiful. The robot is doing some basic maneuvers. It's swimming forward, it's diving, it's surfacing. A couple things to note about the gates. These are real sea turtle inspired gates. They're hand programmed by our biologist collaborator, Frank Fish at Westchester University. So he came out and actually took a flipper and would move it into the correct gate. And then we would smooth that data and kinematically copy it to the other side. And that's the gates. Those are the gates that you see here. So they're non-optimized gates. They're hand programmed by our collaborator. The other thing to note is that similarly to real sea turtles, we're only using the front flippers. So you see the front flippers moving and the back ones are just trailing behind. So you might remember from the video at the beginning of the real sea turtles have these really large front flippers, and then they have very small hind flippers that they only use as rudders. So similarly here, we're not using our hind flippers, but we're currently looking at simulation techniques and gate optimization techniques that would allow us to use all 4 flippers for propulsion and potentially reduce cost of transport in water using that approach. For inspiration, there are not currently any animals that we know of that have 4 equally sized flippers, which we require in order to transition into our terrestrial gates on land. But there's an extinct dinosaur, the plesiosaur, that had 4 equally sized flippers. And so we're looking at the plesiosaur literature and how plesiosaurs swim in order to inspire some of our 4 flipper swimming modes. So we're having a lot of fun with that. Yes? No, so these are really just trailing behind. We're not doing anything with the hind flippers in these videos. We are now, with our newer iteration of the robot, we're doing gate optimization that utilizes the hind flippers, but in these videos, we're not doing any kind of rudder control with them. Yeah. All right, so then we can pull the robot out of the water and morph the limbs from flipper mode into leg mode and take a walk around Yale's campus. So here, the robot is walking right outside of my lab and other places on campus. This is using an upright creeping gait. So this is a quasi-static gait. It's very stable. It means that 3 legs are always in contact with the ground to form a stable tripod while one leg sweeps out to take a step. One thing to note, again, these are not optimized gaits, they're hand-designed gaits, and they're also always walking, the robot's always walking on these rigid surfaces. So you see it's walking on sidewalk and on stone here. This upright creeping gait was very unstable on less stable terrains. So it wasn't stable on grass, for example, or sand, which you can imagine would be a problem if we're trying to transition from land to water environments. So we did program in a third gait. This is our crawling gait inspired by the way female sea turtles actually crawl down the beach after they've nested. They're getting back into the water. So here, Art has its belly in contact with the ground. We're still in leg mode. Our thermoset epoxy is fairly brittle. And so if we put too much force on it, especially in flipper mode, we get cracking. So we left it in leg mode here so we can withstand the forces a little bit better as our robot does an ever so slight push-up and pulls its body forward. And something to note about this video is that I actually took this video myself. So I was really fortunate to do a project at Florida Atlantic University for a while studying the amphibious behaviors of real sea turtles. And so I got to observe many sea turtles that were coming up onto the beach and released on the beach and felt, well, it was wonderful sitting on the beach watching these beautiful animals move. Very validating of my life choices. Yeah. Okay, so let's put it all together. So here we're going to complete an amphibious transition. The first thing that you saw is that Art sits down. So I told you the upright creeping gait, our walking gait, is not stable on granular surfaces. So we couldn't execute it in this environment. So we put the robot there, it sits down, and we go immediately into crawling mode. And so here the robot is going to crawl into the water. And then in a few moments, what you'll see, once it gets sufficiently deep in the water, you'll see the screen blank out and it will say, morphing from leg mode to flipper mode. And then it will come back and you'll be able to see the robot kind of swimming around the shallows at this ocean inlet. So this is an ocean inlet near Yale's campus. It is seawater, but there you can see there's almost no wave energy. It's a really gentle transition site for testing. Very, very low currents as well. And you can also see that the robot is tethered. So off the screen here, we do have a generator. There's a whole generator powering the system. And we're also using the tether for communication. We have a laptop off screen and we're communicating the gates and transitions through teleoperation. Okay, so the reason that the screen blanked out, the reason you didn't actually see the morphing behavior is because we were doing this testing in the winter again. I don't know why we're always doing field testing when it's cold outside, but you can see when the video pans out sometimes, you can see that there's no greenery in the background. Everything looks pretty dormant. We were doing this testing in March of 2021, and it was very, very cold. It was cold air, cold water. And then you might also remember that our morphing is thermally dependent, right? We require unsoftening based on heating our limb past the glass transition temperature of our thermoset epoxy. And that was very difficult to do in this cold, cold water. So we actually took the robot out of the water, morphed in air, and then put it back in the water. So I went to my program review that year in May, and we presented this to our program manager. And he was, really supportive, really great, said, this is, I can see your vision coming through. You're getting really far, but this coupling to the environmental temperature, the fact that you can't morph your limbs in cold temperatures is a really big problem. So let's try to address that. So we said, okay, we can do that. So the first thing we did is we just went back when it was warmer. And yeah, so this is the exact same spot. You saw the robot just sit down. It's crawling into the water. The greenery in the trees. There was a canoe that went by. It was really pleasant doing this testing. We still found, as you can imagine, the water doesn't warm so quickly. Even in the summer, the water is pretty cold. And so we still found it to be really the cost of morphing, the cost of changing and heating our system underwater was so high. And so we developed this strategy that you just saw here where we partially get into the water and then we lift the limbs and morph them in air. And now, because the robot is partially submerged, it's lesser forces as we continue crawling into the water and swimming away. But this still wasn't a perfect solution to our problem. So I will tell you about how we solved this more long-term. But first, I just want to address the cost of transport and the energetics of multi-environment locomotion, since that's what we initially, sorry, are we running low on time? I see, okay. Okay, sorry. Okay, I will try to speed through the rest of this. Yeah. So this is cost of transport versus body mass. Here you can see our amphibious robotic turtle in crawling mode, walking mode, swimming mode. And then you can see a bunch of other robots on here. Cost of transport is not the most commonly reported metric in the literature, so I can't say that this is the most comprehensive comparison to benchmarks, but it is everything that we could find. And really, we wanted to show not that we had a lowered cost of transport in either environment. We weren't optimizing cost of transport in water or on land, but we wanted to show that using our morphing propulsor, that we could get a comparable cost of transport to robots that have been designed for only those environments, only for water or only for land. And I think that we achieved that here using our morphing propulsion system. So this is, but this is also only reporting cost of transport, terrestrial cost of transport and aquatic cost of transport, and does not account for the cost of morphing. So we don't see the energetic cost of getting between those things. And multi-environment cost of transport is something that we're trying to formalize and report right now. And then of course, I'll point out real sea turtles and pond turtles, land turtles, which have a better cost of transport, giving us something to always strive for. So, okay, let me try to fly through just a couple. I'll skip through some slides, but I want to just show you quickly how we address this longer term issue of decoupling from the environmental temperature. So we traded out our variable stiffness material. We pulled out the variable stiffness epoxy, and we instead put in layer jamming systems. So that's the additional tubing that you can see. This is our jamming amphibious robotic turtle. We call it JART for short. It does have a redesigned limb. You can see that it's a little bit, the limbs are a little bit thicker. We lost some of the hydrodynamic profile. So the swimming gates are only paddling gates at this point and not lift-based propulsion strategies. But we do gain a lot in terms of terrestrial locomotion here. We have 2 layer jamming pouches that use a topologically patterned kirigami approach in order to get favorable bending stiffnesses that accommodate our limb strategy specifically. And this is our newest iteration. So that was generation 2, which is currently in revision. So hopefully going to appear in the literature soon. And this is our generation 3. It's completely untethered. So we have everything on board. There's no tether anymore. All power and communication is on board. We are communicating wirelessly via Wi-Fi. We've also got a low-level AI algorithm on board for terrain classification. We've just built a library of terrains that the robot will encounter, and then its limbs, stiffness, shape, and gait based on those terrains. So when it sees it's heading into a terrain, it will autonomously adapt to that terrain as programmed by the library. We also have a refined jamming limb where we've taken out the 3 external actuators and replaced them with a single internal actuator. And that actuator reduction allowed us to reclaim the hydrodynamic profile in flipper mode while retaining the benefits in terrestrial mode. We also have onboard buoyancy control. And these are just some videos of the robot moving on different surfaces that I won't talk about in detail. I will say that the robot is now trotting instead of walking. So now we have 2 legs in contact with the ground versus 3. And so this is a much lowered cost of transport in terrestrial mode. And this is the robot just doing a transition from crawling to standing, which is something that we found really challenging for a while. You've seen in a lot of videos, it's very easy for us to go from upright standing to crawling because we're just falling. But going from crawling to standing is quite a bit more challenging. So we programmed in this kind of downward dog yoga and style inspired pose in order to stand the robot. And this is something that we did. We had to bring the robot to, or we were privileged to bring the robot to a conference in California last year where we didn't have water access. So we wanted to demonstrate the robot walking and then going into crawling and then showcasing flipper motions in air and then coming back up into walking. We didn't want to have to pick it back up and stand it back up every time. It seemed to kind of detract from the autonomous transitions that we were going for. So this was really helpful towards that goal. Okay, so these are my last slides. Just kind of overview, I was able to tell you about a couple of our projects today, robotic skins and our amphibious robotic turtle. But of course, all of these use some of our materials that we've innovated for these purposes, our variable stiffness materials and our actuation materials. Lots of them are liquid metal based, and those come through a little bit more in some of these other topics. And this is the overall vision that we're striving towards. I'm really excited about this idea of adaptive morphology, and we've kind of coined this term of adaptive morphogenesis. We recently published this paper in Nature Reviews Materials that has the same title as my talk today, Robots That Evolve on Demand. And adaptive morphogenesis, we formally describe as unified structural and actuation systems that can adapt in their overall morphology toward changing tasks and environments. But it's been adopted by the community. Lots have kind of put this idea of that it's evolution on demand. And of course, that is directly inspired by this untapped bio-inspired adaptation strategies of looking at evolution as an inspiration for morphology changes. We can think about the terrestrialization of animals, how they went from water to land and how that happened over such long timescales, but that using emerging technologies and materials, we might be able to achieve those types of behaviors very energetically efficiently and on much, much shorter timescales, potentially outpacing the evolution of animals and potentially informing how animals could evolve and how we might help them evolve in the future and push them towards survival strategies in our rapidly changing world. And so with that, I want to thank my group. I'm so fortunate to work with this magical group of people. My students and postdocs are so creative and clever and collaborative and wonderful to work with, and I appreciate them very, very much in all the work that they do. I want to thank my funding sources, and thank you for your attention.
I know we're a little bit behind time, but if you have any quick questions, you can just one quick question.
That was lovely. You mentioned in the first project at the end that you envision using these, for example, maybe on Mars, to pick up soil and create real robots. Of course, there's the problem of radiation.
Oh, yes.
And, polymers don't like radiation, as I'm sure you know.
Right.
So have you thought about that? And do you have in mind they'll just last for a little while and then you'll just build new ones? How are you thinking about that?
Oh, that's a great question. And the honest answer is that we haven't given rigorous thought to it. So I'm definitely aware that polymers don't like radiation and that radiation in the Martian environment is a very, very large challenge. I know that there are groups who are working on this problem, polymers being designed. There's more chemical synthesis groups that are working on polymer design that would be more resilient to radiation. And I'm hopeful to consume those breakthroughs in the future. But as of now, it's not something that we have rigorously tackled, rather a challenge that we're well aware of that we'll have to think about in the future. It's a really good point.
Such a wonderful talk. My question was on, I think you slides, but I was wondering about like the degradation over time. So how many demos of the turtle, for example, in water could you get if you had replaced it for this or even robotic space?
Yeah, that's a great question and an important one. What is the resilience of these systems? I will say that once we switched from epoxy to layer jamming and our variable stiffness materials in the turtle robot specifically, that the longevity of our limbs increased by a lot. We had a lot of issues with cracking of the epoxy, and that would break the whole limb. We'd have to make a new one, reattach it. With the variable stiffness, well, I didn't get to say all of this. It's a much more energetically efficient way of switching stiffness. It's much faster. It's so fast even that we can change stiffness as part of the gait cycle. So you can imagine things like stiffening during the power part of a stroke and softening during the recovery part of a stroke. So that's something that we're interested in, but it's also great for recovery from failure. So when layer jamming systems fail, it's through buckling. And all we have to do is allow atmospheric pressure back in so that the layers can slide past one another and reset, and it doesn't break the whole limb. We just have to reset the limb. So it's helped very much with that specific problem. Of course, the polymers do degrade over time. Sometimes we get stuck in rocks during field testing and we get some, cuts and lacerations on the surface that we have to kind of fix up. Our more prevalent issue is probably with flooding of our motors in the Jetson. So we continue to struggle with waterproofing of our system. During our current grant increment, we're actually trying to prepare the robot for deeper missions. We're trying to prepare it for missions at 10 meters of depth and being able to withstand those hydrostatic pressures. And that is the most common failure mode, is the waterproofing issues and flooding of our more sensitive systems versus actually degradation of the polymers.
All right, well, let's thank the speaker one more time.
Thank you.